Welcome, Dmitry Groshev.
Yeah, thank you. Well, hello everyone. You know what? I like Lego. In fact, I think most of you like it too. And what makes it so fun? I think there are several qualities. First, it's approachable. Everyone can start playing with it, and yet it's deep. So you can build elaborate things with it. So you start with a small, simple car, and then you can use structural engineering, planning, CADs, and all that stuff. And that's also composable, obviously. So you compose blocks in different ways. And those three qualities, I believe, make it fun. So-called amateur cryptography, or pop crypto, is somewhat similar to Lego, except that blocks are way more different. Some blocks fit well with each other, while other blocks blow up in your face when you combine them in the wrong way. So I like geeking out over cryptography, and I want to share my fascination with you today. So first, I will introduce some blocks, some basic blocks to you. Then we will play with them and help our friends Albert and Bertha send cat pictures to each other. Secretly, of course, because it's cryptography. Finally, we will try to learn from that journey and apply that knowledge to our everyday life, everyday professional life. Yeah. So let's start. Basic building blocks. Well, it's customary to start with history. So I believe you all know what this is. It's the most famous cryptographic device there is. It's called Enigma. And despite being one of the most advanced cryptographic machines in history, mechanical cryptographic machines, electromechanical cryptographic machines, right? It was still broken by Allied forces. And I think it means that a better approach is needed. Moreover, there was a new development, right around that time. Computers. So classical cryptography and classical cryptanalysis relied on analysis of patterns in human speech. So and those patterns don't exist in purely digital data. So it also became possible to implement more complex cryptographic schemes, and also computers made cryptography software. And software you can easily share and distribute, unlike physical Enigma machines. So it can even be printed on a T-shirt. Sorry for somewhat bad quality, I wasn't able to find a better one. But it has an RSA implementation on it. There was a story about export controls from USA that at some point cryptography was considered a weapon technology, and its export was controlled. So some people proved their point by printing stuff on their T-shirts, and so, well, look at me, I'm exporting military technology by wearing that T-shirt. So that was the beginning of modern cryptography. And what makes it modern? Well, it relies on security proofs and precise definitions. And so we first need to define what security is. And here we will have some math, but just little. I believe we will have some intuitive understanding of what secure means. But the problem is that security is somewhat multifaceted, and we need a more precise definition to work here. So let's start with what secure cipher would mean. And we all like perfect things, and perfectly secure cipher will mean that it's somewhat mouthful, but also simple, that probability of any message M being encrypted to ciphertext C by cipher E under key key, but that part is not important, is the same across all messages and ciphertext. Or in the other words, you have no information at all about which text was encrypted given the ciphertext. So they're all the same. Like the probability is the same. It makes sense, but there is a serious problem. You can show that for cipher to satisfy that requirement, the key should be equal in length to the message itself, and that's not very useful. Or bigger, but not shorter. And that's a problem, somewhat, but fortunately there is an alternative definition, and it's called semantic security. And it's less mathy, and also, actually, we can formulate it through a game. Let's say we have two agents, the challenger and the adversary. So the adversary is a bad guy, and he tries to break our cipher. How the game begins? Adversary creates two messages and of equal length with like any content that he or she wants, and send them to the challenger. The challenger then flips a coin, and if it's tails, the challenger encodes the first message, and it's tails the second message. And then it sends the result to the adversary. So at this point, the adversary should guess which message was encoded. If there is no adversary that can reliably guess which text was encoded, then the cipher is secure. I think it makes some intuitive sense. Because, in other words, the difference between adversary guess and totally random guess should be negligible. So there's no way to tell which message was encrypted. It's a little bit different from the previous one, because in the previous one, we talked about probabilities, and here we talk about capability to distinguish. It's a small difference, but it makes a lot of, it makes a lot of difference. So it's also very straightforward. The cipher is secure if no one can provide an efficient adversary. If you can distinguish between ciphertext somehow, the cipher is not secure. And you can notice that this definition is not constructive. It doesn't help you to construct a cipher or construct an adversary. And this means that the best way to verify that our cipher is secure under that assumption, our basic blocks are secure, is to just try to break it. If no one can break it in 10 years, then probably it's secure. But we can never be sure. One of the most well-tested ciphers is AES. And what is AES? You probably heard that abbreviation, but it's a very simple thing. It's a function that takes 16 bytes of data and transforms it to another 16 bytes of data. And it also takes key. It does it by shuffling bits around according to the key. So it's all it does. Transforms 16 bytes of data to another 16 bytes of data, and it's one of the simplest building blocks around. It's not that useful, of course, by itself, because your data is usually longer than 60 bytes. So now we will try to implement a secure communication scheme using AES. And for that, we will imagine three people. Albert, Bertha, and Emma. We are in Germany, after all. Albert and Bertha want to send cat pictures to each other, and for some reason they want to do it in secret, while Emma tries to intercept their communications and see the pictures. All communications between Albert and Bertha are public, so they decide to use cipher to encode it. Let's also make it simpler and tell that Albert and Bertha somehow got a shared secret key, because key distribution is a hard problem itself, so we'll skip it here. So what is the simplest way to encrypt a picture using an AES? that I've shown before. And the simplest way is just to split it into 60-byte blocks and encrypt each one of them and then merge them together. And it makes a lot of intuitive sense, and it's simple. It's trivially parallelizable, but there is a problem. So you can see that there is a tux there, and that's the problem, because if blocks are the same, they will be encrypted to the same encrypted block under ECB. So the pattern of similar blocks will tell you quite a lot about the underlying message. And in case of this picture, well, you just see it. Like, we can do better. And I think it's just not right to skip the most classical encryption mode, that is cipher block chaining, or CBC for short. It's almost as simple. The only difference is that you take a previously encrypted block and you XOR that plus there is just XOR of two vectors together. So we are chaining blocks together, XORing each encrypted one into the next one. And that's why it's called cipher block chaining. Obviously, we need to start somewhere, so we also have some static block called IV, or initialization vector. And this construction means that each new block will be encoded to a different result, even if they are similar. So the result will be like this. You can see anything here. But there's still a problem, because if you encrypt encrypt the same message twice, you will have something like this. And you probably can't see there, but those pictures are identical. And that's a problem, because now Emma knows that Albert sent two identical pictures, so we are not totally secure. And for that, there is a solution. Because if you think about it, we need to modify our encryption process somehow, so the ciphertext will differ, even the plaintext are the same. So the most obvious way to do that is to use a unique IV each time, that initialization vector that we used. It should be unique each time. And there is a name for such a unique value that we use on each next message, and it's called nonce. Originally, the name came from the linguistics, but we can think about it as only use it once, like an abbreviation. It's helpful. Nonce is a value such that a pair of key and nonce is unique across all encrypted messages. It isn't secret, so we can transmit it in the clear, and we will need it. Well, actually, we will need to transmit it in the clear because we will need it to decode the message. Like we can't decode it without it. And when we use AES-CBC, that chaining way of using AES, our nonce is an IV. So to properly encode using AES-CBC, you need to generate that IV each time. Yeah, this way we can be sure that Emma will not be able to notice that Albert sends the same cat pictures every day, for some reason. So now we are able to send relatively small cat pictures secretly. Good job. But what if Albert wants to send multi-gigabyte full HD videos of his cat? There is a problem there because as you can see, in AES-CBC we are chaining blocks together, so we are doing it in a sequential way, and we can't parallelize them. Well, it's impossible because we are doing it sequentially. So again, we can do better. And so there is another encryption scheme that is even simpler than CBC, and it's called counter mode of operation, or CTR. It's trivially parallelizable. You just take a nonce, take a block counter, like you're counting blocks like 1 by 1, 1, 2, 3, and so on. You concatenate them into one block, and you encrypt that. You get some value that has no plain text in it yet. And you XOR that into plain text. It seems kind of risky, but it's perfectly safe under the assumptions that we operate on. So you can also notice that encryption and decryption will be completely symmetrical. Like they're the same actually, because when you XOR something twice, you just cancel the thing that you XORed. So also in CBC you need, well, CBC can operate only on full blocks, and that padding that you will need to add is really tricky to get right. So CTR is way simpler in this regard. So it's better even in this sense. But as you can guess at that point, there is a pitfall. What happens if you use the same nonce twice? Well, if you use the same nonce twice, you will get something like that, something like the third line. So when if x is that thing that you XORed, then you can just XOR two ciphertexts together, and you get suddenly you get XOR of plain texts. And for English language, it's kind of trivial to restore both texts if you have XOR of them. So in fact, it's almost as bad as no encryption at all. So we have a trade-off. Either you have a very simple algorithm that is trivial to get right, but you have to think about how you use that nonces, or your encryption will be slightly broken, subtly broken. It will not be slightly broken. Yeah, or you can have a CBC that is sequential. It's hard to implement right, but IV reuse is not that bad. And actually, it's not a trade-off because you can get both, but it's still too early to use the algorithms that are both nonce misuse resistant and parallelizable and so on. But in a few years, we'll have them. And actually, it was surprising for me because I thought that symmetrical encryption is something like really simple compared to asymmetrical encryption and all that tricky mathematical stuff. But somehow, at this point, we still not have a totally, well, we still don't have a cipher with all properties that that we want to. That we might want, but well, we just don't have it at this point. Yeah. So now let's look at things from a different perspective. What if Emma can intercept and modify messages on the fly? What if she knows how the encrypted data looks like? So let's say Albert sends a picture of cat to Bertha. He also adds a note that says, "Look at this cute cat. What can Emma do?" If we encrypt under CTR, we can do a magic trick. Because even though we don't have a key to the cipher and we can't decode it, we can modify the ciphertext in a way that will make it decode to a value that we want. So if we have like plain text cat and we use CTR on it, so we XOR each byte with a key, and then we XOR it with XOR of the text that is there and the text that we want to be there. Then we will get the text that attacker wants on decryption. So in other words, encryption does not guarantee that no one tampered with that text. And this property is called malleability, and we can fix that. But your instincts of using hash or CRC will not help here because the attacker can modify that hash or CRC too. So we need a new building block here. And that building block is called MAC. And there is a family of crypto functions called message authentication codes. They're similar to hashes, but they also take a secret key, so you can't reproduce that hash without the secret key. So you can construct a MAC from a hash, and it will be called HMAC. So there are hashes like MAC, HMACs, like HMAC SHA-2 that is made from SHA-2. Now we can guess that we can finally secure our communications by encrypting the image and all the captions, like encrypting everything with ASCTR, for example. Then we compute HMAC over it and concatenate that hash and the knowns to the message. So we can say that HMAC authenticates the message. It proves that whoever computed the hash value had a secret key. And so there is a term for such an encryption. It's called AAD. That means authenticated encryption with additional data. And that additional data is that authentication tag and nonce. There are also, we constructed this mode from a basic building blocks, and there are modes that work constructed as AED from the start that are a little bit more efficient than first encrypting than computing a hash. For example, ASGCM. And also see this competition called Caesar. It's about new AED modes. Right. So I have a little puzzle for you, but I don't have enough time. So yeah. Maybe in the end I will give that. So I hope our little journey with Albert and Berta made you appreciate how complex encryption can be. So what can we learn from this? At least 3 things, I believe. First and most important, I don't know about you, but I don't always write stuff that requires crypto in it. But when I do, I like to avoid silly mistakes. So there is a contradiction here, and I believe the only way to avoid those silly mistakes, is to just like it and enjoy like that pop cryptography, because it's, well, most people don't do that every day. So it's like it can work just as a general interest. So when you get home from this conference, please do one of 2 things. Either subscribe to Cryptography by Stanford University on Coursera, or you can also check out CryptoPals. It's a set of crypto challenges. And if learning by doing is your thing, do the second one. Or even better, you can do both. Another thing that we can learn is to follow best practices, because there are subtle differences between different approaches that are not obvious. So if we have some ready-to-go formulas about what to do, it's nice to have them. So, and surprisingly, one of the best list of advices I've seen was on a GitHub gist. And you can find it by looking for updated cryptographic right answers. And there's also an interesting discussion on Hacker News about it, and I think you will find it as well, like just by looking for that title. Yes, and finally, the best thing is to minimize that screw-up surface, so to speak. So most crypto libraries out there, including Bouncy Castle for JVM and so on, are collections of primitives, and they don't really prevent you from screwing up. So this was the reason why Daniel Bernstein, some time ago, wrote a library called SALT, well, sodium chloride actually, but SALT, whatever, with the simplest possible interface. You have a crypto box where you can put your data and get your data back, or get an error. Just 2 functions, basically. It's the simplest interface possible, and the only thing that you should care about is not screwing up the nonce. But way less choices than when you use Bouncy Castle, for example. As always, there is a catch, because you see, Daniel Bernstein is a scientist, and this may or may not be the reason why the library exists as a tarball on his website. So it was forked by another people and called libsodium, and the fork added more stuff, making it a bit easier to screw up, but the fork is on GitHub, and it's well supported, and it has very nice documentation, so you're still better off using it. And a little thing that you need to be aware of both salt, right, and libsodium are written in C. This means that you will need to use JNI, and you will need them on your system. But I think it's not that bad. Finally, let's talk some Clojure. So here's a list of Clojure libraries for secret key cryptography that I was able to find. Surprisingly, there are only 4 of them. And the first one is had no commits for quite a long time, and also it has a very simple interface, like just encrypt and decrypt, which is nice. But as its algorithm, it uses ASCBC without authentication, and we learned that it's not a good idea. Another one, body core, is again, it's really nice. It's well supported. Its last commit is this year, but it's bindings to bouncy castle. But the problem is that there are like it's not guiding your hand. Like there are a lot of stuff there, so you can make the wrong choice without knowing it. The third one is deprecated, so let's skip it. And the last one, cesium, is actually a bindings to Lipsodium, and it's very well written. It uses GNI, and there is another reason why I like it. And this is the first crypto library that I've seen with emoji in the source code. You may not see it, but it's a magic emoji there, def macro magic. So if you need to encrypt something, this is the way to go. Also, you can check out the author's blog on lvh.io. I think it's pretty cool. Finally, it was a long journey, and we started from the beginning. That is, what does it mean to be secure, and what AES is. Then we tried to help our friends Berta and Albert secure their chat. We've tried different ways of encrypting data, and we've seen how they fail. We've learned about AAD, and finally we do some lessons from our journey and apply them to Clojure and like everyday life, professional life. So I wanted to reflect on how things fit together. As I said, it's like Lego, but some blocks are made of wood, some are made of helium, and some are made of plutonium. And so it's quite tricky to combine them, but also intellectually rewarding. And finally, you know, they say don't invent your own crypto. And I think that we all should invent our own crypto, because otherwise we will do that inventions in production, which is way worse. Yeah. So thank you all for having me. And we have a little bit of time left, so I want to give you that puzzle. So, because we'll have some microphone around here, so it will be convenient to try to find what's wrong. So you receive data from the internet.
Hang on a second. Yeah. We can either take the puzzle or the questions, but not both.
Okay. Let's start with the questions.
Not both.
Yeah. Okay.
Just say.
It wasn't exactly. So which one of the libraries should we like? Are the other
Cesium.
Cesium, but the other three we shouldn't use then. Is that your opinion?
Well, if you have some legacy system,
yeah.
Then the best bet is Bouncy Castle because it's old and well tested and so on. And the body core seems like a nice binding to Bouncy Castle.
Okay.
So if you have to implement to support some old crypto, it's a nice choice. But if you implement something from scratch, it's way easier to use that Cesium library because the interface is very simple.
And the other one you shouldn't use as well?
I don't think so because one is deprecated and another one, like there are 4 of them, and the body core is that kitchen sink type library,
okay.
and another 2 are deprecated or wrong, like they don't authenticate the code.
I think I'm just more curious about your insight more than anything. So I think we're all kind of aware of like the web frameworks and how many stars that those things get. Yet, presumably, you're going to be encrypting something if you're using like a backend framework. Why do these have such few stars?
I don't know. I think it can be related to that point that I made, that most people don't do that on a daily basis. So it's like it's a thing that you do once or twice or like a few times in your professional careers, but the consequences of errors can be quite bad. I mean, you're implementing, you're encrypting a cookie and you don't authenticate it, and it means that anyone can modify that cookie, and it's not trivial to know that even if cookie is encrypted but not authenticated, it can be modified successfully. So, yeah, so I think this is the reason why they have not many stars, because for professional reasons, not a lot of people would look for them, but the meme of cryptography being quite fun is not that popular. So, yeah.
Last question.
As you said, as a programmer, you don't work with cryptography on a daily basis.
Yeah.
If I have to, and I choose one of the libraries, and I encrypt my strings, do you have any hints on how I validate that everything is working correctly? Because I'm not the mastermind hacker who can debug my own cryptography.
Yes. So the only I think. Well, there are two ways. First, we have to first we have to trust professionals at some point. Yeah. On the other hand, we can look for preprints of attacks on particular algorithms if you are paranoid enough. So, well, you can just look for attacks on IIS, for example. Well, and on a most everyday basis, it's just use salt to see lipsodium. I think it's the simplest advice, because they are made with minimizing the chance of error in mind. Yeah. So I will be here. So that puzzle I can tell about it after the official part.
That's great. So first of all, thank you.
Thank you.
And this is your applause.